So this lecture is about creating an anomaly detector using neural networks. We want to do this in an unsupervised manner. So remember, in supervised learning, we have our data, but each item in your dataset needs to be assigned to a label, either a class or a continuous value. We call this target, which we want to predict. In the case of anomaly detection, this can be a binary target indicating an anomaly or not, or a continuous value, so an anomaly score or RUL score. RUL stands for remaining useful lifetime. Given that labeled data, a model is trained. In this case, a supervised one, because we tell the model to replicate the underlying hidden function using the supervised labeled dataset. There are more unlabeled than labeled datasets available, therefore we want to get rid of the boss. But it turns out this is not a trivial task. So look at this time series, for example. It is an accelerometer-based vibration dataset which is attached to a bearing. One vibration axis is shown in red and one is shown in blue. So how can we predict if the bearing is in a broken or healthy condition? In this case, I'm telling you that the bearing is totally fine. So let's have a look at a dataset from the faulty bearing. Hard to tell, isn't it? So let's zoom in a bit and check again. So on the top we see healthy data, and at the bottom we see the faulty one. At least we can tell that they are different. So we are using our biological neural network in our brain in order to see this. So what if an artificial neural network can do the same? So if our brain looks at two different time series plots, it's able to spot the difference. In theory, we can implement an artificial neural network doing exactly the same. A convolutional neural network, for example, can look at the two plots and tell whether they are different or not. To be honest, I haven't tried this, so maybe that's an exercise for you. But what we can do is using an LSTM, a long short-term memory network, for time series analysis. Remember that the LSTM is Turing complete and ideally fits time series and sequence data. But isn't there a problem? Since this is unsupervised machine learning, we don't have labels available. So the task of a neural network is to take X and adjust the weights that it reconstructs Y. But we don't have Y. So hopefully you remember what the autoencoder does. So an autoencoder is using X as input and output as well. So an autoencoder will try to reconstruct what it sees on the left-hand side on the right-hand side. And if you now train an autoencoder with an LSTM and healthy data, it tries to reconstruct the healthy data. And remember that it runs through a neural bottleneck. And once it's trained, it will have a hard time to reconstruct faulty data. That's the point. That's how the anomaly detector works. But how do we know if we are currently showing healthy or faulty data to the model? So this is quite simple, because in a real-world scenario, there is much more healthy data than broken one available for training. So if we randomly pick a sample, the chances are very high that it is healthy data. And the chance is of course very low that we pick faulty data. There are much more sophisticated strategies behind that, which are often domain specific. Therefore, we won't dive more into details here. In the next module, we will implement an LSTM autoencoder based anomaly detector using Keras. So stay tuned.